In this video, we're going to take a closer look at linear interpolation. Interpolation is a mathematical tool or method that we use to calculate an unknown value, particularly when we know values to either side of the unknown value. Interpolation is often used in science and engineering, and in finance, we use it to calculate unknown interest rates. For instance, we may wish to calculate an unknown interest rate where we have two known interest rates on either side of that unknown interest rate. In this video, we're going to use a hypothetical scenario and solve for an unknown interest rate. In the process, we're going to use first principle methods and calculate this interest rate. But as we go along, the aim is to create a general formula. So we'll extrapolate a general formula from the application that we'll do so that we can have a general formula for similar scenarios that we look at in the future. What is the hypothetical scenario we're going to look at? Well, we're given the following rates. For 90 days, we have a deposit rate of 3.5%, and for 180 days, we have 4%. What we're going to do is draw a line from the 3.5% to the 4% point, a straight line, which is why we call this linear interpolation. And just keep in mind, in the back of your mind, there are more advanced methods to do interpolation. We could have used more points and fit higher order equations like a quadratic equation or cubic equation to allow for some curvature instead of just a normal straight line. In this scenario, it's going to be linear interpolation, just a simple scenario. So let's look at the scenario. We've been given these four different data points, and two of these are each associated with one another. The first thing we're going to do is assign the 90 and the 180 day values. So the day values, we're going to say those are X values. And the interest rates, the 3.5% and the 4%, we're going to say those are Y values. Why are we doing that? Why do we wish to do that? Because the day values are values, those are independent variables. And we're going to plot this in two-dimensional space. So those are the days. As we plug in the day value, it's going to spit out and transform or give us a interest rate value. So in other words, the Y value is the dependent variable, if we had to view this as a function, in other words. And what we're going to do is we're going to plot this in two-dimensional space. So we're going to have, first of all, an X and a Y axis, where we're going to now plot these different values according to their location on here. So in other words, it's just two-dimensional plotting. The 90 days interest rate of 3.5% will be a 1 point on this graph, and the 180-day value that's associated with it is 4%, will form another point on this graph. We said we're doing linear interpolation, so that just means, just to visualize it, we're drawing a straight line between these two different points. The problem we're solving is we're asking at 125 days, this is an unknown interest rate, but we know what the day value is. So if we fire in 125 days and draw two parallel lines from there, what is the Y value that will come out of this? And when we know what that Y value is, we've solved the problem that we posed in the beginning of this. We've solved a hypothetical scenario. Our next step here is, in order to be able to form a general formula and to apply some math on this, we need to assign all of these different data points to different, or give them names, variable names. And the names we're going to use very simply are the following. We're going to call the 90-day X value X1, the 125 X value X2, and the 180-day value, you guessed it, X3. So associated with each of those X1, X2, X3 values are Y values. So X1 is associated with Y1, which is 3.5%. X2 is associated with Y2. We don't know what the value is. That's what we're solving for. X3 is associated with Y3, which is 4%. The next thing we need to do is calculate the values associated with this straight line. And the formula for a straight line is what we're going to call up next. In other words, Y is equal to mx plus c. We're going to zoom in on this M here. We're highlighting M here because M actually represents the first thing we need to solve, which is the slope of the curve. M is the rise over the run. Or another way to represent it is delta Y over delta X. Delta representing the change in. So the change in Y over the change in X. What does that mean? What is the point of that? Because the rise over the run, as X changes, how will Y respond? That's what we want to solve here. So delta Y over delta X, in our scenario, we're going to use the known data points to solve this. That will be M is equal to Y3 minus Y1 divided by X3 minus X1. Let's use our values to solve this. Y3 is equal to 4%, Y1, 3.5%, X3, 180, X1, 90. So this is purely a calculation to say, well, the change is happening in Y divided by the change in X. And we solve from here, we're going to get the value M is equal to 0.0056%. That's fantastic because what that tells us now is that as X changes by 1 day, the associated change in Y will be 0.0056%. Let's return to our linear equation. Y is equal to mx plus c. Let's now zoom in on mx. In this instance, mx is going to be 0.0056%, which we just calculated to be, times x is the change in y. What we wish to is, as x changes from 90 days to 125 days, that's what we want to know what's going to happen to y. So we plug in, and delta x, the change in x in this instance, becomes the one we're solving for, 125 minus 90. That reduces to 35 days, or simplifies to 35 days. So mx is 0.194%. It's 0.0056% times 35 days. Because we know 1 day change, 0.0056% rise in interest rates. It's a positive change. 35 days, it's going to be 35 of those. 35 of those is 0.194%. Back to the scenario again. Y is equal to mx plus c. In our scenario here, we now know what mx is. Mx is 0.194% plus c. But what does c represent? Well, what it means is, in our scenario, we can substitute our values, the variables that we've assigned to this, into this equation. And that gives us, we're not solving for y itself, we're solving for y2, which means y2 is equal to 0.194% plus y1. So c gets replaced by y1. And the value of c is 3.5%, which means y2 is equal to 0.194% plus 3.5%. That tells us the value of y2 is 3.694%. And we could stop here. We've solved the problem. But what we wish to do is derive a general formula to be able to apply in future scenarios. So what did we do? Let's take a retrospective view in terms of how can we build a very simple single formula to solve this equation without doing all these different steps in the meantime and reasoning through everything. The reasoning part's obviously crucial. We do want to do the reasoning part. But how can we do it in a single step with one formula much more effectively, knowing now what we do know? What we have established is that the change in y from y1 to y2, in other words, from 3.5% to this y2 value, which we're solving for, is given by the change from x1 to x2 multiplied by the slope. So we can generalize that into a formula, and that would be that y2 minus y1, so the change in y, will be equal to the slope multiplied by the difference of x2 minus x1, that change in y that we had there, from 90 to 125 days. Knowing that, this equation is we wish to solve for y2, so we're going to manipulate this equation by moving the y1 over to the right-hand side. In other words, we're isolating y2. That's what we wish to solve for. y2 is what? y2 is that m times x2 minus x1 plus y1. The next step we do is we're highlighting m again in purple here because we know how to calculate m. M is calculated simply as y3 minus y1 divided by x3 minus x1, because those are the outside points, the known variable, the known points. In other words, still the same starting point, but where is that known point? It was 180 days, we had 4%. That's how we calculated the slope. So what we do next is we plug that part, that purple equation, into our big equation itself, or into this general equation, and we end up with y2 is equal to x2 minus x1 times y3 minus y1 over x3 minus x1, all of that plus y1. That is a general equation we need to solve this in one step. So to prove that, and to just do it all full circle, let's plug in the values that we had from our hypothetical scenario and prove that we can solve this in one step, or simplifying steps, but in one formula. First of all, we have the change in x from the x2 minus x1 is 125 minus 90 times m, which was 4% minus 3.5% divided by 180 minus 90. That will give us that 0.0056 plus all of that plus 3.5%, which is the y1 at the end there. We can go through a couple of simplifying steps. We don't have to. 125 minus 90 is 35. The difference between those, the slope is 0.5%. There's a change of 0.5% in 90 days, which means that y2 is now equal to, another simplifying step we would take is that 35 times 0.0056 plus 3.5%. The 35.0056 was 0.194. And we added 3.5% to that, and that will give us a final answer of 3.694%. We could have done a lot of those simplifying steps in one step as well. But there you have it. There's a general formula to solve for linear equations where we're dealing with interest rates. And this is how we apply linear interpolation.